Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Actually, this one would be a very brief review on our chapter 17, which is retaining wall design. Okay, let me share my screen with you. So this is the figure for conventional retaining wall. It could be either angle face wall, or it could be vertical face wall. Okay. Now, the design methods we will follow here is basically Rankine's method and Coulomb's method. And then you will have like active pressure analysis and passive pressure analysis for both these two cases. But primarily, you will see that most of the cases we design conventional retaining wall based on active situation. Okay. Now we have to remember that these three things are important for different type of retaining walls. What is that things? These are vertical face or angle face. We are talking about this face here. Okay, this face here. This is vertical face. This is angle face. Then retain soil type and slope of the retaining soil. Retained soil type means like whether this one is granular fill or siffy soil. Okay, and then slope of the retained soil. This is basically the slope of the retained soil. If the retained soil is along that horizontal line, then we call that one flat slope or zero slope. If it is an angle alpha, then basically we call that one a slope, or inclined slope. Okay. Now let's see the first thing that how we can apply the theories that what we learned from Rankine's active and passive pressure theory to design our retaining walls. So for Rankine earth pressure theory, the lateral force work on a vertical line. I'll just show that one here. You can see this is the line here. This is actually the point at the located at the edge of the heel of the base slab. So we usually go to this point either here or here. Then we just draw a line from a vertical to the surface, okay? From A to the vertical line, which will intersect with the top surface at point B. So we assume that the active force will always work on that line AB here. Okay, line AB here, the line AB here. And AB is the height of the wall. Okay, the AB is the height of the wall. And the active force is always assumed that this is like a vertical line here. It doesn't matter whether this one is vertical here or inclined here. So that's the case. So whatever is your shape of your retaining wall, you always have to assume the face is vertical, okay, to find out your active pressure. Now you have to remember that the whole thing at the left side here, including that wall as well as the soil, will be part of the analysis, like procedure. So here you can see that not only the wall, but also the soil left of the point of the line AB must be considered for your stability analysis. Okay, so you have to just remember three things here. First of all, you just draw the line from A to B, and your active force will be working on the line AB. So all the time we'll assume that the back face is perpendicular. Okay. then your H may be higher than your actual H here, okay? This height of AB is basically considered the height of the wall, okay? Not like from here to here. In that case, you can see this is a flat slope. So in that case, height of the wall is equal to AB. But here you can see actually AB is a little bigger than the height of the slope. So here actually all the time we have to consider the height is from A to B, okay? The first thing. What is the second thing? All the weight, including this wall and the soil, must be considered for stability analysis, okay? So anything left side of the line AB is included in the stability, including the wall and the soil, okay? And the active force is usually parallel to the line, top line here. If it is flat, then this one is flat. If this one has an angle alpha, then this one has an angle alpha here. And it always works at 1/3 of the line AB. Okay, 1/3 of the line AB. That's why this one is working. So that's the first thing to find out how we can find out the active force for Rankins method. Now, if we go for, let's say, the Coulomb's method, then basically you see here, actually we are showing here that how we can just calculate the stability analysis against overturning, okay? So this is overturning. You see that wall, this one is trying to go like this. So if you take a moment here, actually the driving moment, if it is bigger than the moment that's created by the weight of this whale and the vertical force here from the active force, we have to just compare that one and see whether this structure is stable or not against overturning, okay? So your factor of safety against overturning has to be summation of moment that trying to resist that movement, and this is the summation of moment that's trying to drive that overturning, okay? So you can see here, basically the factor of safety against overturning should be 2 or 3, and the overturning moment you can see here, that's basically pH multiplied by h by 3. That's actually trying to rotate. So you have to take a moment here, and this horizontal force pH multiplied by the h by 2, that's actually trying to overturn that one. On the other hand, you will see the weight of this soil as well as the wall, that's gonna try to resist. At the same time, the PV, which is the vertical component of your PA, that will also try to resist the like overturning. So you can see here the resulting moment here, and definitely like if you have any soil here, sometimes we have a very small amount of soil in front of the wall. In that situation, we can ignore our passive pressure. Otherwise, we have to consider the passive pressure too, because if you take a moment, then you can see the passive pressure is also trying to rotate clockwise, like moment, okay? So if you see here that this one is clockwise, the weight of this whole structure is also clockwise, and the PV is also trying to rotate that one clockwise direction, where pH multiplied by the 1/3 of the H prime, that's actually try to rotate that one counterclockwise. So the counterclockwise rotation moment is basically here is the driving moment, and the moment that's trying to resist that one is clockwise moment with respect to point C here, okay? So you can see from PV, your MV is basically from PV multiplied by the distance from here to here, which is nothing but the width of the wall, B, that's what we are trying to show. And then the weight of soil and structure, that's basically like for each of the structure, this one is the, like showing that the total weight multiplied the centroid of the total weight, that's basically your moment coming from the weight. Now let's see. As I said, like this is your resisting moment. When you plug all those values in your equation, you can find out your factor of safety. Now we'll be talking about the stability against the sliding. Okay, that this is the picture for sliding. Okay, this one is trying to push this way the horizontal force, which is basically the pH. Then basically some force has to resist that one, so this one doesn't move this way, right? That's, you can see this one has failed here because of the sliding. Okay, this retaining wall has failed because of the sliding of the base. Now let's see here that what is the way we just try to do that one here. You can see the factor of safety against sliding is basically summation of forces that's trying to resist the movement, and the factor and the summation of forces that's trying to drive that force here. So if you see the horizontal force working here, then basically you can see this is the pH is basically trying to slide in the other direction, where this one, these two forces here, PP and R, that's basically trying to resist that one. Now, what is R here? R is the, like the interaction between the soil and the bottom of the wall here. Okay. Now you can see here the resistance force R, which is basically tau multiplied by A. This tau is basically the tau between the shear strength between the soil and the bottom of the wall. Okay. And B into 1 is basically the area, B is the width, and 1 is like per feet or per unit length of the wall. Okay, so you can see this is tau, which is B into 1. Now, what is tau basically? We know that tau is sigma tan delta prime plus the cohesion here, like the cohesion here. Okay, cohesion between, that's soil and the wall. That's coming from the cohesion part. And then there is a frictional part, which is basically sigma prime tan delta prime. And most of the time we assume that delta prime is like varies from half to 2/3 of your phi prime. At the same time, your CA or cohesion between wall and soil, that also varies from half to 2/3 of the cohesion of the soil here. Okay, we are talking about base soil now, not the field soil. Okay, this is refill here. After constructing that one, we refill that one, but this is basically the foundation. In your last exam, I saw that many of you actually confused with this soil and this soil. Okay, this is the foundation soil. So you have to consider this foundation soil for actually sliding and bearing capacity. On the other hand, this soil is responsible, like the soil here, the weight of the soil, as well as responsible for creating the active force along the line AB. Okay, so two different soil, refilled soil, and this is the foundation soil. This is sigma 1, phi 1, C1, and this is sigma 2, gamma 2, phi prime 2, and C prime 2. So this soil here, which is actually here was the ground level, this side of the wall, and this is the ground level in the other side of the wall. So when you do your stability against sliding and bearing capacity, you must have to deal with this soil here. Okay. Now let's see So the total horizontal resisting force, that's basically R plus PP. So that's your R plus PP, okay? And you can see if you just play with that, your sigma prime is basically your summation of V divided by the area here, right? That's the normal force working here. So summation of V divided by the area, which is actually B into 1, and then your tan delta prime plus CA prime plus PP. So if you see here that B cancels with this, so basically your total horizontal resisting force is summation of V tan delta prime plus B. B is the width of the wall. C is the cohesion between soil and the bottom of the wall. And this is your passive force that's coming from here. Many cases, actually, if this depth D is small, then basically we can, like ignore PP. But in your exam, if I don't tell you that, hey, ignore PP, then basically you have to consider that one, okay? Now let's move forward. So horizontal driving force that's coming here, that's basically your PA cosine alpha, okay? PA cosine alpha. And then your factor of safety would be this divided by this, okay? Now let's see that what would be your stability against bearing capacity, okay? And the thing is, like, the soil here can fail sometime, okay? That's the fail due to the loss of bearing capacity of the soil supporting the base, and then it may undergo deep-seated shear failure like this. The most common one is basically this one here, okay? Now let's see how this one works. So the factor of safety against bearing capacity failure can be determined from FQS is equal to the ultimate bearing capacity of the soil divided by the maximum pressure that's coming from the wall, okay? Because you will see there is always some eccentricity on the wall, okay? Since the wall is, long, so we can consider that one as a stiff footing, and you'll understand that your eccentricity would be always in one direction, in the B direction, basically. Now let's see. We usually require a factor of safety of 3 against the bearing capacity failure. Okay, now let's see that how we can analyze that factor of safety against bearing capacity. So you can find out your ultimate bearing capacity of the retaining wall based on this one. You can see that I took the shape factor out from there because the shape factor would be 1 because it's a stiff footing. Your L is much bigger than your B, so all the shape factors are 1, so I just ignored that one. And you can see that since the wall is continuous, so this is shape factors are 1, and it's only one-way eccentric, okay? If you see that diagram here, then basically your summation of V is working at a distance like X bar from, this is basically all the weight of the soil and the concrete, okay? So this is the, include this one plus the part of the, like vertical component of this active force. That's basically your summation of V. But you can see your V is working here, whereas the middle of the bottom of your foundation is here. So this is basically your eccentricity here, okay? That's your eccentricity. So you can see since this one is working here, so this one has much higher pressure than here. Now, If your E is greater than 1/6, then basically this one will be less than 0. Okay, at 1/6, this one has to be 0. So if we see the Q mean is 0 or less, then basically we have to change the size of the wall. Okay, we have to change the size of the wall. Maybe we have to just increase that one a little bit more in this side. Okay. Now, how we can find out this X bar here? So this X bar is basically summation of moment, resisting moment, minus the summation of overturning moment, divided by summation of V. Then basically you will get your X bar from there. So your E is B divided by 2, which is basically from here to here, minus your X bar from here to here. So you get your E from there. Okay. If your E is greater than 1/6, then consider a different section. Okay. Your Q is equal to gamma 2D. Okay, here. This is your gamma 2D, and your B prime is B minus 2E because this is a one-way eccentricity, right? Once you get that one, then basically you can start filling your, start calculating your depth factors. Shape factors are 1, but depth factors will be changed. So you can just see that one from here, and you will see always actually your, there is an inclination here. Okay, so you have to find out the inclination factor too. You always will have inclination because this force, horizontal and vertical force, may not work at the center of the, most of the time it's work here at a distance E. So we can just try to find out what angle this one is making with the vertical to find out our psi naught. Okay, I'll show that one, like how to find that one there. Now your maximum pressure or pressure at here, that would be summation of V divided by B into 1 plus 6E by B. And your minimum pressure would be summation of V divided by B multiplied by 1 minus 6E by B. Okay, so if you see this one is actually much higher, much smaller than the bearing capacity, then basically you are fine. So your bearing capacity factor would be basically your QU divided by your Qmax. Okay. Now I'll just show an example here that how we have to find out like the force that's working along that line. This is the second part. Maybe I'm not going to discuss that one here because we discussed that one in our actual lecture. So if you open that one, you can see that one. I'm just trying to review this part here because I see that in our last exam, many of you made like severe mistakes here. Okay. So this one is saying that determine the magnitude and direction of the active force on the wall as shown in figure 1 based on Rankine and Coulomb's method. Okay. So let's start with Rankine's method. So if you see Rankine's method, so first of all, we have to find out, hey, this is the corner here. So we have to draw a line from here to all the way to the surface, right? So this is our point A, and then I have to draw that line here, and this one intersect at point B there. Okay, so now we can assume for simplicity that the active force act on the line AB, which also implies that the back face is vertical here. Okay, now we see that from here to here is 2 meters because from here to here is 2 meters, right? And we know this angle, so we can find out what is that height here. So that's what we try to see. This is 210 degree, which is 0.35. So the total height of line AB would be 1 plus 5 plus 0.35, that's 6.35, okay? Now you can see this is the 1/3 of your h bar by 3, which is 2.12, means like the active force will work on that line here, okay? So 2.12 from the bottom, and for phi equal to 34 degree, which is 34 degree, and your alpha equal to 10 degrees, and your back face is vertical. Very careful about that. Back face is vertical, even though the back face is not vertical, but for simplicity, in rankings method, we always consider this one is vertical. So try to find out your Ka from the table 16.3 or equation 16.33. Okay, I'll show that one in the chart, that how you have to find that one. Okay, in the next page. Let me finish that one first. So your PA would be 0.5 Ka gamma h squared. So you can see this is 106.8 kilonewton per meter. So this is 106.8 kilonewton per meter, and that one is working 10 degree, means like parallel to the surface here, okay? And the height from here to here is 1/3 of AB. Now you can see, we can just find out the horizontal and vertical component of this active force. So this angle is 10. So basically, this is your PH, which is, and this is your PV. When you can see this one is basically 105.2 kilonewton, and this one is 18.6 kilonewton. Okay. Now the rest part, I'm not going to discuss that one here, but I'm just going to show you how to find out from table 3 your Ka. So this is your alpha 10 here, and your phi equal to 34 degree. So you can see this is your Ka 2944. That's what we used here. Okay. Now, Coulomb's method. Actually, I missed that Coulomb's part there. Let me go back there and show you that what we do, like for Coulomb's method here. The simplification. Let me see, most probably I missed that one somewhere. Okay, let me start talking about like the Coulomb's method. Like Coulomb's method, we don't have to draw any line AB here. For Coulomb's method, all the time, the force work at the back face here. So whatever is the back face, if it is vertical or inclined, you always have to consider that one, like to find out your, your active force based on Coulomb's method. You can also remember that Coulomb's method is only applicable for granular soil, so your C has to be 0 all the time, backfill soil here. But the soil here may not be like the sandy soil or granular soil. Here, soil could be definitely the actual soil, like the foundation soil. Now, what is the difference? Other differences here. You can see that if you have alpha here, then basically for Rankin's method, the force is always working parallel to this line, means like making alpha degree with the horizontal. For Coulomb's method, that's not true. Okay, let me show you this one here. That first of all, we have to find out what is the angle of the back face here, which is beta here. Okay, so this we can find that one like tan inverse 6 divided by 2, that's 72 degree. Okay, now your delta prime is 2/3 of phi prime. So if it is 34 of 2/3, that's 22.7. Okay, now you can see from the table, I can find out for beta 72, phi equal to 34, alpha equal to 10 degree, and delta prime is 2/3 of phi. So we can go to table 16.6 or equation 16.36, and we can find out our Ka from there, which is 0.481. One of the other difference here is like, since we don't draw that line AB here, so basically any soil will not be part here. Any soil here will not be the part of your stability analysis, okay? And whatever is the height from here to here, it doesn't matter. The height of the wall would be always equal to this height. Like here is 5 plus 1, 6, like 6, okay? So let me show that one here. So your PA would be equal to 0.5 Ka gamma H square, that's your gamma, and H is always equal to from here to here. Okay, you don't have to add this one here. Okay, for Coulomb's method, no. Now you can see the force here, 155.5, that's actually working like 1/3 from the bottom of the wall, which is 6 divided by 3. So this is like 2 meters just above the, like bottom here. Now, what is that angle here? Okay, this is very, very important. I see that like many of you was very confused when I asked that question in your second exam. This is not alpha here. This alpha is only for Rankin's method. What about the Coulomb's method? Actually, for Coulomb's method, we try to find out this angle from here. Okay, if this is 72, this angle is 72. So we have to draw a line perpendicular to this back face. So if we draw that line perpendicular to the back face, that has to be 18 degree because this is 72. So this is 72. If this is perpendicular, then this is basically this is 72 and this is 18, total 90 degree, right? And this force, Coulomb's method, this Coulomb's active force is always make delta degree with the perpendicular line. So what is that delta? That's 22.7. So this one is making 22.7 degree with the perpendicular line. So basically your total horizontal, like angle with the horizontal is this plus this, which is basically 40.7 degree. Okay. Now your PH means like the horizontal component of your PA has to be cosine of this angle. Okay, so it's 118.1 kilonewton per meter. So this one is 118 kilonewton per meter. And then basically your PV is PA sine 40.7 degree. So this one is basically here. Okay, so that's the way we try to find out what would be our horizontal and vertical component of our of our active force. Okay, so these are two different methods. It's completely different. For Rankin's method, every time it assumes that this one is vertical. We just draw from the heel a line to the top of the surface, and we think that the active force is working along the line AB. On the other hand, for Coulomb's method, the active force is always working at the back face of the wall, okay? So that's the biggest difference. The other thing is, whatever your alpha, your total height doesn't change in Coulomb method. On the other hand, in Rankine's method, your total height changes if you have any alpha here, okay? And the final difference is like for Coulomb's method, we only take the weight of the wall, not any soil included here. On the other hand, in Rankine's method, we not only include the weight of the wall, but also the line. If I draw the line AB, any soil within AB and the wall must be included in your analysis, okay? That's basically the thing, but I'm going to show you like in table 16.6 or equation 16.36, which is basically added in your spreadsheet. If you want to use that one, you are most welcome to use that one. That take much, like shorter period, because I see that some of the students are trying to solve the actual equation, which is much, much bigger. And most of the time, after spending like 10-15 minutes, I saw that they're like 90% time they came up with the wrong answer, okay? So I'll just request you to use either the table or the spreadsheet I provide you so that you can very quickly find out your KA for both Rankine's and Coulomb's method, okay? Now I'm not going to talk about this one anymore because we just discussed that one in our actual lecture. So you can just take a look and then try to see how to solve all those like stability or factor of safety against like different situation, okay? So I'll stop it here. And if you have any question, do not hesitate to send me an email, okay? Thank you for your attention.